Hi, before I start, I have a confession to make. This is our latest offering, the Dynatrace Hypermodal AI, but I must confess I'm not exactly sure what the hypermodal in the name stands for. But I do know pretty well what it does, and this is what I'm going to explain to you today. So hi, my name is Martin. I'm from Dynatrace, and I'm going to talk about machine learning for observability today. To set the context a little, Dynatrace, our software, allows customers to monitor all aspects of their customer-facing applications, with ultimately the goal to just making sure that it works smoothly, no frustrated users. Our typical users are large companies, and some of the largest companies in the world are actually our companies. These are just a few examples. Okay, so what do I mean exactly with observe or monitor the applications? This is the so-called Dynatrace architecture. Let's have a look at the various aspects. So for one, we observe the infrastructure that our clients are using. So that means actual physical hardware, computing elements, for example, in a data center of a cloud provider. This would mean monitoring things like CPU load, disk storage usage, and so on. Then observing the application of the clients themselves. So is it working? Is it responsive? What are the response times? The third aspect is security. So here there are actually three different things that we watch out for. One is to protect the software of our client from any kind of threats. The other is to analyze any kind of threats or incidents, whether they have been successful or not. The third component deals more with marketing and business related aspects. So digital experience follows the user experience through the software offering, through the application of our client. So that means from some aggregated numbers, drilling down really to individual user journeys, so recording each click of a customer on the website. Business analytics extracts relevant business numbers from the vast amount of data that we are collecting. Automation is an important aspect. Examples for that are automated alerting when something goes wrong, or in the best of worlds, before something goes wrong, and then automated workflows to actually act on these alerts also automatically and solve them before any human being actually ever notices. We also have a couple of additional custom solutions that we offer, and all of it is integrated in our so-called platform services, where the different components of our software live. Okay, so much about that. So our software is for the largest companies in the world. You might be wondering, what is in it for you then? Is this of interest? Should you be listening to me? Or should you rather check your email during this presentation, wait for the next talk? Well, I want to show you that there is actually something in it for you. One thing is that I believe observability is for everyone. Also in the research sector, computing resources that are used are getting bigger and bigger, not just in the context of large language models, but in all kind of fields. So this might actually be something for you. And we do have a free test version that we also offer, so just check it out. Maybe more interesting for the audience here, research collaborations. As member of the research lab at Dynatrace, it's actually in our mandate to seek collaboration with other researchers in particular, but not only, also academic institutions. So if any of these topics appeal to you, if you're already working on that, get in touch. Maybe we can apply for common funding from our side as industry partner. Maybe we can find other ways. Lastly, I'm going to show some real-life machine learning use cases to you, which I think are simply interesting by themselves. In addition, maybe also in context with the above with collaborations. Okay, let's look at our machine learning related offering. It's called Davis AI. It consists of three different components, each of which I will tell you more about in just a second. So there's the predictive AI part, the causal AI part, and the generative AI part. The predictive AI part deals mostly with forecasting. The task of the causal AI part is, whenever there is a problem, to actually find out what caused this problem. Yeah, the generative AIs acts like a glue of these different components, gets info from there, and then produces some very specific artifacts, which I will be talking about in just a couple of minutes. But first, let's go to the predictive AI. So predictive AI deals with forecasting, I already told you that, and related anomaly prediction. Why is this important to us? Imagine a customer who's running a web application on 5,000 disks. This is not uncommon. Yeah? At some point in time, 3 of these disks actually might be getting almost full. Now, one of two things could happen. A, nothing happens for a while, the disks run out of disk space, and then the application starts failing, users get frustrated, start complaining. At some point, the administrators notice, they fix the problem, and things are back to normal. That would be called reactive resource management. The second possibility, due to our forecasting, we already predict that 3 of these disks will run out of disk space soon, and we send a report to the owners of this service, which they act upon, in most cases in an automated way, maybe also manually. They request more disk space, and the problem is solved before any users ever notice. This is what is called predictive resource management, and this is of course what we strive for, and the possibility that our software gives to our customer. How does this work in practice, this alerting? Let's say we are observing a value. This could be the response time of a website. We have some measurements plus a confidence interval and a baseline. We notice for a while several of these data points that we collect, so as a function of time, are consistently above the baseline. That means the baseline is violated, and we send out an alert. Yeah, someone receives them, it's acted upon manually or in an automated way. It is fixed, and the response times go down again below the baseline, and we can de-alert. So I think, yeah, that looks very simple, fairly straightforward. You would think you don't need really anything very sophisticated to do this kind of thing. But yeah, reality is slightly more complex. Look at this picture. This could be a typical customer who's running 100 applications, web applications typically. Each of them uses services, maybe around 100 in average. Each of these services runs in average on 10 hosts, so on different locations in the world, some redundancy. On each of these hosts, we then deploy 10 different containers, and in each of these containers, 10 different processes are running. So this is not an uncommon example. This means 10 million processes that we could monitor. And in addition, there are about 10 to the 3 metric types that we observe for each of these processes, metrics that we can observe. So that means in total we could be observing 10 to the 10, that's 10 billion different time series. Now you can imagine what happens if only in very rare cases we send out false alerts. Even if the frequency, if it's just out of this 10 of the 10, a few every second, a few per mil every second, we would still end up with hundreds, thousands, tens of thousands alerts every second. They would just drown everything, would produce noise. Our customers would get annoyed. They would miss the actually interesting alerts. This simply, would not work. So you see, we need to do things. First of all, everything needs to be automated. It's not possible to send 10 to the 10 alerts by hand manually. And it needs to be super robust, super reliable. We need to really drill down on the number of false alerts to almost nothing. While of course we still want to make sure if something does happen that we send out an alert. We don't want to miss that either. How do we do that in a slightly simplified picture? This is the workflow for our forecasting. First, we validate that the data that is coming in is proper according to some metrics. Then we select an algorithm to fit the data. This could, in simple cases, be a linear forecasting, maybe because there is not much variability in the data. Maybe we simply don't have enough data to tell, or maybe all other things simply fail. So that's kind of the fallback then. But the more common thing is that we do a seasonal forecasting. What does that mean? We try to extract seasonal patterns from our data. Typically, seasonal patterns that our customers see are during work hours versus during night, if it's, for example, traffic on a website, but also weekdays versus weekends. Then we have time and calendar features. That would be Black Friday versus an ordinary Friday. So once we've extracted these patterns, we perform a so-called probabilistic regression. So that gives us a forecast not only for data points, but also for the uncertainty of these data points. This is what the probabilistic refers to. Using the result of this regression, we can then do a Monte Carlo based sampling and get a central line plus uncertainty intervals. Let's have a look how this looks in practice. So in black, this could be the data points that we are collecting. You can see these 5 peaks. This would be office hours, while the valleys in between is during nighttime. And you can see between 5 peaks and then the next peaks, you have the weekend where there's also less traffic. Okay, so we could now run our regression. This is what we get as a fit, as a forecast for the future in red. And now, whenever the black in the future stays within the red, we are good, we are within the baseline. If this is not the case, then given some conditions, we send out an alert. Typically, this is set automatically. But in the interface, the customer could also say a manual alert that would like that. In this very example, the alert would be set such that if there are 3 baseline violations in a time window of 5 minutes, then an alert is sent out. Okay, things get a little more complex in practice. We don't really have a baseline, but a base cube actually, so there are different dimensions to the problem. For example, the geolocation of the user or which browser he's using, which operating system. So, and all this then for 10 to the maybe up to 10 to the 10 different metrics. So it really has to work in a very robust, reliable, and automated way. That's the important thing. Okay, the second component of our machine learning offering is the causal AI. Here the task is to tell what is the actual cause of a given problem, to understand what it is and what we actually mean with problem. Let's have a look at the lifespan of a problem. So in this example, the problem first appears on the infrastructure layer. So that means an actual PC, a computing element, maybe a disk breaks. This would affect a service that runs on this infrastructure element. It also starts malfunctioning. Then other services also running on this same host also start showing problems. Eventually, the application itself is affected and users start experiencing errors. Yeah, this is when also this would be brought at latest to the attention of admins. They would investigate. And the task of root cause analysis of our causal AI is then to find out what is the root cause of this problem. Problem being the application failure, and the root cause in this case being on the infrastructure some host which is not behaving properly. How does that look for our customer in the interface in a slightly simplified view? You can see here again a website. In red it's indicated that there is a problem with it. You can see the different layers, the application layer, service layer, process layer, host layer, and data center layer. And then you can see the connections between different elements on different layers. And this is what really distinguishes the Dynatrace software from everything else and also from our competitor, that we get this complete picture of the architecture in a fully automated way. The client installs our software, our one agent, on their computing element, and then it observes, and after a while you get this whole architecture. And using this, things get a lot simpler, or even start to get possible really. You can see the connections, how the website is connected to services, those two processes. We can see 2 of the processes also shown in red, so there's a problem. Both of them run on the same host, which also has a problem. So very likely this host in this case is the root cause that is causing the problem. So in practice, or again slightly simplified, what are the steps of such a root cause analysis? First, we detect a problem. For example, the website is slow. Then we analyze the problem. That means understanding the topology. So from that we know the website depends on some certain front end, and then we have a look at this front end and we observe, okay, the front end is also slow. We continue on this topology. This front end depends on a certain back end, so we check out the back end. Okay, the back end is also slow. We go further, the database running on that back end is also slow. The host on which this database runs is actually okay, so that's not a problem. So it seems like the database in this time here is the root cause. So again, this looks fairly simple, but it only is if you've solved already two problems. One is this topology problem, but the other thing is, what does it actually mean something is slow, and how do we figure that out? Let's have a look at an example again here. Let's say, okay, the front end is slow. What does that mean? We figured it out via so-called change point detection. Change point detection is related to anomaly detection. Anomaly detection finds points which are unlikely given a certain model, so outliers. Change point detection, on the other hand, tries to figure out at which timestamp a model changes into a new model. So when does the underlying model change? Let me illustrate that. Say we observe these light blue data points. It could again be a response time. You can see the points are roughly distributed in a Gaussian way. Then something happens and the response time moves up. It's a lot longer now. Still, the data points are distributed according to some Gaussian roughly, but it's a different Gaussian. It has a different mean clearly. So it's a different model that describes the data. At some point, the problem is fixed. The model goes back to its original state. And the task of change point detection is now to figure out these red lines. So in time, when does the change take place? Okay, so finally, I'm coming to the third component of our AI offering, and that's Davis Copilot, our generative AI. I already told you that the generative AI part uses information from the predictive AI and from causal AI, so the forecasting, the anomaly detection, the root cause analysis. It, of course, also has other inputs. First of all, the user input, the prompt, the question. Also, the customer-specific data from its data lakehouse, and whatever the pre-trained large language model already knows from its very pre-training. Okay, these are the inputs. What are outputs? Outputs, in theory, can be unlimited, but a few of them, the ones that we focus on, are, for example, a query. It could be a dashboard that is generated. It could, of course, simply be an answer to the question of the user. Okay, let's have a look at some examples, some use cases. First, productivity and onboarding. So imagine a site reliability engineer who has been on holidays, comes back to office on a Monday, tries to figure out what happened during his holidays. So now he has two options. He could go through dashboards from last week, maybe even through log files, or he could spin up our Davis Copilot and simply ask any anomalies last week and immediately get the answer. Last week, two anomalies were detected, and then a description of this analysis. So you see, this is not something that the engineer could not have figured out also in other ways, but in this way, of course, it was a lot quicker. It increased his productivity. It increased his efficiency significantly. Let's have a look at another use case. So here the user asks, what is the service level objective for the search API in the last 4 hours? Okay, the answer here is interesting. So first, the very question is answered. It's 99.9.8% uptime. But then the answer is actually enriched with information from the documentation, exceeding the target of 99.95% uptime. So this comes from the documentation. And as a third component, actually a visualization is also offered to the user. Okay, so let's move on to maybe our most important use case at the moment, that is query generation. In Dynatrace, we have our own query language that our customers can use to query their data. The Dynatrace query language, DQL, you can think of it as something like SQL. That's good enough to understand what I'm going to show you here. So one example here, the user could ask, show the top 5 Kubernetes nodes by CPU. What is the reply from Davis Copilot here? It's a query, as we would hope for. In this case, it's still fairly simple. It's only 5 lines. Still, of course, it's a lot quicker than typing this yourself. Plus, you don't need to know by heart things like dd.kubernetes.node.requests_CPU describes the variable that you're interested in. Okay, and then you just click on Run Query and you actually get the result, in this case also in a nice visualization. Let's look at a slightly more advanced example. Question, how many users were impacted by yesterday's outage? Of course, the large language model cannot know this by itself from its training, so it needs data about what happened to this customer yesterday. So in a first step, our Davis Copilot enriches the prompt with information about this problem, and then the actual query is generated. And you see, this one is already a lot more complex. It's 25 lines. Let's be honest, a typical user would not be able to produce this query. Only a very advanced user could do that, and even then they would probably spend 15 minutes, 20 minutes, I don't know, to produce a query like that. Here it's just with, entering a couple of words, again, huge productivity gain, and then just click Run Query and you get your answer. Okay, the last example I have for you, use case dashboard generation. So here the user asks, create a dashboard for critical Black Friday services. The answer, as we would like to see, is then this actual very dashboard with interesting quantities. That's already very neat, but if you think about what happens behind the scenes, I think it's even more impressive. First, the user asks, okay. Then the generative AI bot, the large language model, needs to understand that question, so get the semantics right, and then figure out what information does it need to answer this question. So it needs information from the causal AI about current and past status. It also needs information from the predictive AI, particularly a forecast for the behavior for a high load scenario, because that's what a Black Friday is. It's a high load scenario, right? And then again, generative AI kicks in, puts together all this information and produces the output for the user. In this case, the dashboard. Okay, before I close my talk, let me just say a few words about the Dynatrace Research Lab. The Dynatrace Research Lab consists of 4 different departments. Distributed data systems, which is mainly concerned with improving query performance. Real-time analytics, which deals with streaming processing of big data. Cloud-native security, the name is self-explanatory, I think. And generative AI, what you've already heard about today. The Gen AI research topics are large language model query generation, the evaluation of the performance of large language models, alignment, so things like bias and toxicity, LLM fine-tuning and conditioning, optimization of retrieval augmented generation, and the generation of synthetic data. So in all of this, if you're interested in any collaboration on research, please do get in touch. We are very open for that. In addition, also concerning teaching, if you're giving a lecture series and you would like to invite us for one of the events, for example, to talk about an industrial AI use case, then we are more than happy to do so. Just get in touch and we'll figure something out. Open for collaboration. Okay, and if you do want to get in touch, how do you do that? Send me a mail, connect on LinkedIn, or simply Google Research Lab Dynatrace. That's it. Thank you for your attention.